Young's double slit experiment. Light from a narrow slit, capital S, illuminated by a monochromatic source, is allowed to fall on two narrow slits A and B placed very close to each other. The width of each slit is about 0.03 mm and they are about 0.3 mm apart, as you can see in this diagram. Since A and B are equidistant from S, light waves from S reach A and B in phase. So A and B acts as coherent source. Expression for bandwidth. Let small d be the distance between two coherent sources A and B of wavelength lambda. Draw AM perpendicular to BP, as you can see in this diagram. The path difference del is given by BP minus AP and AP is equals to MP, as you can see in this diagram. So del will be equals to BP minus AP. Now AP is equals to MP, so del is equals to BP minus MP. That one is equals to BM. In right angle triangle ABM, BM is equals to D sin theta. We know that if theta is small, then sin theta is equals to theta. So the path difference del is equals to theta into D. In right angle triangle COP, as you can see in this diagram, tan theta is equals to OP upon CO. That one is equals to X upon capital D. So tan theta is equals to X upon capital D. For small values of theta, tan theta is also equals to theta. So in this case, the path difference will be del is equals to X small d upon capital D. Bright fringes. By the principle of interference, condition for constructive interference is the path difference is equals to n lambda. So we know that path difference is given by X small d upon capital D. That one is equals to n lambda in case of constructive interference, where n is equals to 0, 1, 2 and so on. Indicate the order of bright fringes. So we can calculate the value of X is equals to capital D and lambda upon small d. This equation gives the distance of the nth bright fringe from the point O, as you can see in this diagram. Dark fringes. By the principle of interference, condition for destructive interference is the path difference is equals to 2n minus 1 into lambda by 2. We know that path difference is given by X small d upon capital D. That one is equals to 2n minus 1 into lambda by 2, where n is equals to 1, 2, 3 and so on. Indicate the order of the dark fringes. So X is equals to capital D into 2n minus 1 into lambda upon 2 into a small d. This equation gives the distance of the nth dark fringe from the point O, as you can see in this diagram. Thus on the screen, alternate dark and bright bands are seen on either side of the central bright band. As you can see in this diagram, we mention dark and bright fringes. Bandwidth beta. The distance between any two consecutive bright or dark bands is called bandwidth. The distance between n plus 1th and nth order consecutive bright fringes from O is given by xn plus 1 minus xn is equals to d upon small d into n plus 1 lambda minus d upon small d into n lambda is equals to d lambda upon small d. So, bandwidth beta is equals to capital D lambda upon small d. Similarly, it can be proved that the distance between two consecutive dark bands is also equals to capital D lambda upon small d. Since bright and dark fringes are of same width, they are equispaced on either side of central maxima. Condition for obtaining clear and broad interference bands. First condition is the screen should be as far away from the source as possible. Second one, the wavelength of light used must be larger. And third one is the two coherent sources must be as close as possible.